Hello everyone, welcome to my presentation. My name is Bhanu and the topic of my presentation is implementation of processes and threads in Linux. Let's start with understanding how processes are different in Linux. So user element is present in every process and it's responsible for running a user program, right? When one of its processes performs a system call, it enters kernel mode and runs in kernel context with a separate memory map and complete access to all the machine resources. It's still the same thread, but it now have additional power and its own kernel mode stack and own program counter. These are crucial because a system call might become stuck in the middle of something, such as waiting for a disk operation. So the program counter and registers are in Linux are preserved, allowing it to be resumed when kernel mode later. So which minimizes the resource wasted in Linux. The second thing is task struct. The task structure in Linux is used to represent process internally. So, unlike most other operating systems, Linux employs the star structures to describe any execution environment, rather than making a distinction between process like read process and threads. As a result, a single threaded process will have only one task structure, whereas a multi-threaded process will have one for each of the user level threads. Finally, the kernel is multi-threaded with kernel-level threads that aren't affiliated with any other user processes and responsible for running kernel code. We also have a process descriptor of type task struct and is kept in memory for all times for each process. It holds crucial data for kernel's control of all processes such as scheduling settings and list of open file descriptors. So when a process is created, it gets a process descriptor as well as a memory for kernel mode stack. And pointers to other data structures or segments are stored in the process descriptor fields, although sometimes these segments are very relevant when the user process is not runnable. As a result, it might be swapped or paged out to avoid wasting memory. So, and the information about the file descriptor, on the other hand, may be stored in the user structure and brought in only when the process is in memory and ready to execute. And that's how memory is managed in Linux. The last thing is Linux uses PID to identify processes. All the processes are organized by the kernel into a doubly linked list of task structures. In addition to traversing a linked list to get process descriptors, the PID can be mapped to task structure address and process information can be retrieved directly. So now let's understand in detail what information does process descriptor hold in the fields. So first one is scheduling parameters, like it can hold process priorities, amount of CPU time consumed, and together these are used to determine which process to run next. Then we have memory image, which holds pointers to the text, data, and page tables. Then we have signals, like which signals are being ignored and which have been caught, which have been blocked or are stored here. Then we have machine registers, where like when a trap the kernel occurs, the machine registers are saved here. Then we have system call state. So information about the current system call, including parameters and results, are stored here. Then we have process descriptor table. So when a system call involving a file descriptor is invoked, the file descriptor is used as an index into this table to locate the encode data structure corresponding to the file. And next we have accounting. So pointer to the table that keeps track of the user and system CPU time. Then we have kernel stack, which are a fixed tag for used by the kernel part of the process. And the last one is miscellaneous, which holds current process state, even being waived, PIDs of the parents and of the childs, etc. So now that we know what information is there in process descriptors, let's start thinking about how Linux creates a process. So for a child process, a new process description and user ID are constructed and filled out mostly by the parent. The child is assigned a PID and a memory map is created and shared access to the parent file is appointed. The registers are then set up and it's ready to go. The calling process produces a task structure as well as few additional data structures when a system call is made. The PID hash table entry for the new task structure is then updated to point to an available PID, that is one that is not currently used by any process. Because here the semantics of fork state the no memory is shared between parent and child, it should not allocate memory to the child data and stack segment as well as print, print copies of parent segments. But due to high cost of copying data, all the current Linux system offer the child their own page tables, but they also point to the parent pages, which are only targeted as read-only. So next, the code running in the process makes an executing system call with the command named as an argument when startup. The kernel now looks and validates the executable file, transfer the argument and environment string to the kernel, and frees the old address space and page tables. Now one can fill up the new address field. The new tables are set up, the argument and environment strings are then transferred to the new stack. The signals are reset and registers are set to 0. At this moment, the new command can begin to execute. So I put an example for ls command. So when a user types command ls in the terminal, the shell forks off a clone of itself, creating a new process. The new shell then executes to overlay the contents of the executable file ls in its memory, and that ls run. So last topic we have is threads in Linux. So when a new thread was stored in the past, the original threads and the new thread shared everything but the registers. Open file descriptors, signal handlers, alarms, and other global attributes were all per process rather than per thread. But in the year 2000, Linux introduced clone, a powerful new system function. Clone is now available in any other Unix version. So clone made it possible for each of these and other elements to be processed or thread specific. And also we have something called as sharing flag bitmaps. So it is a bitmap that enables the more fine-grained sharing than a typical Unix system. Each of the bits can be set independently of other, determining whether the new thread copies or shares data structures with the other thread. So let's go to them one by one. The first one is clone VM. It determines whether the virtual memory is shared with the old thread or copied. If it is set, the new thread just moves in with the existing ones, so the clone call effectively creates a new thread in an existing process. If the bit is cleared, the new thread gets its own private address space. Having its own address space means that the effect of its store instruction is not visible for the existing threads. Second one is clone FS, which is bit control sharing of the root and working directories of the unmasked flag. Even if the new thread has its own address space, if this bit is set, the old one threads share working directories. Next one is clone files. It is an analogous to clone fs bit. If said, the new thread shares its file descriptors with the old ones, so calls to IC by one thread are visible to the other ones. Again, as normal holds for threads within the same process, but not for the threads in the different processes. Next one is clone Cyan, which enables or disables the sharing of signal handler table between the old and new threads. If the thread is shared, even among threads in different address spaces, changing a header in one thread affects the header in the others. The last one is clone parent, bit control, which who the parent of the new thread is. It can either be the same as the calling, or it can be the calling thread itself, in which case the new thread is a child of the caller. That's all about the threads, and that's pretty much wraps my presentation. Thank you for watching.